Welcome to this NX Insight. I'm Alexis Capone from Janus Engineering, and if you are ready to explore a game-changing approach that reshapes the future of product development, let's dive into simulation-driven design together. Are you curious about how engineers use advanced technologies in their product development to stay competitive on the market? Today's industry is facing a lot of challenges. Engineers and designers must develop ever more complex products by maintaining their quality, reducing the costs and the time to market. In this context, design and validation cycles of a product must be accelerated and optimized in order for their company to remain competitive in a constantly evolving market. Here comes simulation-driven design. Simulation-driven design is a powerful engineering approach that integrates simulations in the design process. It allows engineers to make informed decisions about product performance and design early in the development cycles. But what are exactly the numerical tools and methods behind this concept? In simulation-driven design, the concept of optimization is really important to keep in mind. When the designer creates product variations, manual modifications and requirements checking can be time-consuming and subject to human mistake. In this context, parametric optimization can help the designers to find an optimum solution for their product performance. This method consists of setting up a geometric optimization with variables, constraints, and objectives in order to find the best geometry for a given problem. In this example, this piston engine has an asymmetric component that offsets its center of gravity. By using NX Design Space Exploration module, an optimization cycle is defined with geometric expressions referenced in design features, with the aim of aligning the center of gravity with the axis of rotation. Multiple iterations are running and are stored in a result table. Results can be then filtered, and the best one is highlighted in green to be quickly recognized and applied. When designing a component, it is essential to respect the functional requirements, including the mechanical resistance during assembly or during part lifecycle. Multiple simulation solutions exist in the Siemens Digital Industry software portfolio, from basic linear static finite element analysis to more advanced multiphysics simulation. Let's begin with basic examples. To check the mechanical resistance of a component, you can use NX Performance Predictor module to quickly set up loads and constraints on your model. Thanks to its user-friendly workflow and its new meshless technology, Performance Predictor makes mechanical simulation accessible to designers and provide them reliable results extremely quickly. In this example, this plastic cover needs geometry modifications. Thanks to synchronous modeling capabilities, you can easily modify the position and dimensions of multiple features, even if the body comes from a step import. The performance predictor analysis is then updated immediately and automatically displays the new simulation results. As we have already said, it is interesting to avoid manual iterations when searching for an optimum solution. In Siemens NX, you can combine both Performance Predictor and Design Space Exploration to run mechanical optimization. The objective is then to minimize the maximum displacement or von Mises stress calculated by the simulation. The optimization runs a new simulation at each iteration and stores the results into a table, letting the designer the possibility to choose between multiple solutions, with the best one highlighted in green. When multiple design variables are specified, dozens of iterations are necessary to cover all the possibilities. This method can then save hours of engineering work. The Design Space Exploration workflow is compatible with multiple application cases, from tank-effective volume optimization to the simulation of complex geometric structures, such as this geroid optimization for additive manufacturing. A triply periodic minimal surface with a good compression resistance and a great potential for future 3D printed heat exchangers. Back to conventional use case, Design Space Exploration is compatible with assembly management and product configuration. This is particularly interesting when you must use interpart links, such as expressions or link bodies, in your design process. In this propeller example, an airfoil section optimization is running to create multiple design variations with respect to a mass target. The multiple designs can then be inspected in the results table, and their performance can be validated in StarCCM Plus, a powerful and high-end CFD tool from Siemens. You can as well set up a CFD optimization with the CAD client module for direct dialogue between NX and StarCCM Plus, or even use EADS platform for a high-end multiphysics simulation between multiple platforms. We have seen some examples of parametric optimization, but the concept of simulation-driven design also integrates generative design, which consists of a set of tools allowing the user to directly obtain a natural shape of a part according to its load case. Topology optimization, for instance, is a commonly used method in additive manufacturing in order to optimize the shape of a part regarding its mechanical or vibration load case. It's an interesting approach for structural parts in aerospace or transportation industry, where the mass of a part is a critical aspect in the design requirements. In Siemens NX, you can easily set up a topology optimization in the dedicated module by specifying the design space, material, loads, boundary conditions, and shape constraints. In this example, we want to minimize the mass of this land gear bracket while maintaining sufficient structural strengths. The functional areas are defined according to the fixtures of the part, and several load cases can be defined according to the different use cases. Once the study has been correctly set up, the optimization run automatically converges in a couple of minutes to an optimized and highly smooth 3D shape, ready to be exported to a 3D printer if needed. The result of this run is a 50% lighter optimized part for additive manufacturing, which can be validated or redesigned properly with Realize Shape, the subdivision modeling application of NX. Another generative design solution to decrease the mass of a part is to create a lattice structure. This type of structure is also well adapted for additive manufacturing processes, for applications such as shock-absorbing structures, flexible part design, or in the medical industry to facilitate an implant-bone integration. In this example, this sole structure can be modified with an adaptive lattice density in order to lighten the part and to thicken the lattice on the most stressed areas. This workflow can be automatized in order to quickly create patent-specific medical devices in combination with additive manufacturing technologies. As you may have seen, Siemens NX contains a lot of features to improve your development process, such as topology optimization, performance predictor, or design space exploration. In summary, simulation-driven design is a transformative approach that addresses the challenges of modern product development by accelerating the timelines, reducing the costs, managing the complexity, fostering the innovation, ensuring compliance, and minimizing risks. For companies aiming to stay competitive on today's dynamic industrial landscape, it will become an essential tool to continue to deliver high-end products. Thanks a lot for watching until the end. If you want to discover Siemens NX solution by yourself, you can download a trial version of our software. The link is in the description just below. Don't forget to subscribe to Genius Engineering YouTube channel so you don't miss the next insights coming soon. See you next time!